Welcome! In this problem, we'll explore an interesting challenge from LeetCode, number 1365. How many numbers are smaller than the current number? Together, we'll break down the problem, analyze different approaches, and identify the most efficient solution. Let's dive in. In this problem, we are tasked with analyzing an array of integers, referred to as nums. For each element in the array, we need to determine how many other numbers in the array are smaller than that specific element, and then return the results as a new array. To clarify, the input will be an integer array nums, where each element represents a number. The output will be another array of the same length, where the ith element represents the count of numbers in nums that are smaller than nums, I. Let's look at an example. If the input array is 8, 1, 2, 2, 3, the output will be 4, 0, 1, 1, 3. This means that for the first number, 8, there are 4 smaller numbers in the array. For the second number, 1, there are no smaller numbers. For the third and fourth numbers, both 2, there is 1 smaller number. Lastly, for 3, there are 3 smaller numbers. Now, let's explore this example in more detail. To break down the first example, we analyze each number in the array. For nums 0, which is 8, the numbers smaller than 8 are 1, 2, 2, and 3. That gives us a count of 4. For nums 1, which is 1, there are no numbers smaller than 1, so the count is 0. For nums 2 and nums 3, both equal to 2, there is only one number smaller than 2, which is 1. Finally, for nums 4, which is 3, the numbers smaller than 3 are 1, 2, and 2, giving us a count of 3. Let's move on to another example to further solidify this understanding. If the input array is 6, 5, 4, 8, the output is 2, 1, 0, 3. Here's why. For nums 0 equal to 6, the numbers smaller than 6 are 5 and 4, so the count is 2. Continuing with the second example, for nums 1 equal to 5, the only number smaller than 5 is 4, giving a count of 1. For nums 2, which is 4, there are no numbers smaller than 4, so the count is 0. Finally, for nums 3, which is 8, the numbers smaller than 8 are 6, 5, and 4, resulting in a count of 3. The output array 2, 1, 0, 3 reflects these counts. Now consider a third example where all the numbers in the array are the same. If the input is 7, 7, 7, 7, the output is 0, 0, 0, 0, because there are no numbers smaller than any of the elements. This demonstrates that when all elements are identical, the result will always be an array of zeros. Finally, let's look at the constraints and edge cases for this problem. The array nums will have a length between 2 and 500, and each element will be an integer between 0 and 100. These constraints mean that we need to ensure our solution is efficient, especially for larger arrays. For edge cases, if all elements in the array are the same, the output will always be zeros, as no number is smaller than another. If the array has only 2 elements, the output will either be 0, 1, or 1, 0, depending on the order of the numbers. Since the input size can be as large as 500, brute force solutions may not be optimal. Instead, approaches leveraging sorting techniques can provide better performance and are worth considering for this problem. To start, let's consider the brute force approach. The intuition behind this method is straightforward. For every number in the array, we count how many other numbers in the array are smaller than it. We achieve this by iterating through the array for each number and comparing it with every other number. In terms of implementation, we initialize an empty result array, and for each number in the input array, we maintain a counter that increments whenever we find a smaller number during the inner loop. This counter is then added to the result array. While this approach is simple and easy to understand, its time complexity is n squared, due to the nested loops, which makes it inefficient for large input sizes. On the bright side, it requires very little additional space, making it space efficient if we ignore the result array. However, its inefficiency limits its practicality, especially as the size of the input grows. The brute force approach, while simple, has a significant drawback. Its quadratic time complexity makes it highly inefficient for larger arrays. To address this, we can use an optimized approach that leverages sorting. The key insight here is that in a sorted array, the position or index of each number directly corresponds to how many numbers are smaller than it. With this idea, we can reduce the complexity of the problem. First, we create a sorted copy of the original array. Then, we use a dictionary to map each unique number in the sorted array to its index, which represents the count of smaller numbers. Finally, for each number in the original array, we simply look up its count in the dictionary and append it to the result array. This eliminates the need for nested loops, making the solution much more efficient. Analyzing the optimized approach using sorting, the time complexity is O, n log n, dominated by the sorting step. The subsequent operations, such as creating the dictionary and traversing the array, are linear, contributing O, n. This gives us an overall complexity of O, n log n. In terms of space, we require additional space for the sorted copy of the array and the dictionary, resulting in O, n, auxiliary space. The benefits of this approach include its efficiency for larger inputs and its ability to handle duplicates seamlessly. It's also relatively easy to implement. However, it does require extra space, and while it's faster than brute force, it isn't the most optimal solution in scenarios where the input range is constrained. This brings us to an alternative approach using counting sort, which is even more efficient under certain conditions. The counting sort approach is based on the assumption that the range of numbers in the array is small and fixed, such as 0 to 100. This allows us to use a frequency array to count occurrences of each number. The key idea is to first populate this frequency array so that each index represents the frequency of a number. Then, we compute the prefix sums of this array, where each index now represents how many numbers are smaller than the corresponding number. Using this prefix sum array, we can directly determine the count of smaller numbers for each element in the original array. This method is extremely efficient, with a time complexity of O, n plus k, where k is the range of numbers. The space complexity is O, k, for the frequency array. While this approach is highly efficient, its applicability is limited to cases where the range of numbers is small and predefined. Given these approaches, we select the optimized approach using sorting as the primary solution. This approach strikes a balance between efficiency, simplicity, and versatility. While the counting sort method is faster, it is constrained by the need for a small, fixed range of numbers, which may not be a valid assumption in all cases. On the other hand, the sorting-based approach works for any range of numbers, handles duplicates effectively, and is straightforward to implement. Though it has a slightly higher time complexity than counting sort, the O, n log n, complexity is generally acceptable for a wide range of inputs. The brute force approach, despite its simplicity, is rejected due to its inefficiency for larger arrays. Overall, the sorting-based solution is a practical choice that balances generality and performance. When comparing the trade-offs between these approaches, the brute force method is the simplest but becomes impractical for large inputs due to its O, n squared, complexity. The sorting approach, while slightly slower than counting sort, is much more general purpose and easy to implement. It works across any range of numbers and handles duplicates seamlessly. Counting sort, on the other hand, is the fastest solution but is limited to cases with small, fixed ranges of values, making it less versatile. Considering these factors, the sorting approach emerges as the most practical solution, offering a good balance between performance and flexibility for a wide range of problem scenarios. To solve the problem of determining how many numbers are smaller than the current number, we can explore multiple approaches. One of the simplest methods is the brute force approach, where we count smaller elements for each number by examining all the elements before it in the array. Here's how this process works. First, we initialize an empty result array, which will store the count of smaller numbers for each position in the input array. For example, if the input array is nums equals 8, 1, 2, 2, 3, we start with an empty list, res equals. Then, for each number in the array, we iterate through all the elements before it, checking how many of them are smaller. This involves two loops, an outer loop to pick the current number, and an inner loop to compare it with all prior numbers. Let's break this down step by step in the next part of the explanation. For each number in the array, the brute force approach compares it with all the numbers that come before it. To do this, we initialize a counter, count, to 0 for the current number. This counter keeps track of how many smaller numbers we find during the inner loop. Then, for each previous number, if it is smaller than the current number, we increment the counter. Once the inner loop finishes, we append the value of count to the result array, res. For instance, in the array nums equals 8, 1, 2, 2, 3, when processing nums 3 equals 2, we compare it with the numbers before it, 8, 1, and 2. Here, only 1 and the earlier 2 are smaller, so the count becomes 2, and we append this value to res. Finally, after processing all the numbers, we return the result array. The pseudocode for this approach outlines the steps clearly, with a nested loop structure where the outer loop iterates through each number and the inner loop counts smaller elements. Let's walk through an example to visualize the brute force approach. If the input array is nums equals 8, 1, 2, 2, 3, we process each number one by one. For the first number, 8, there are no elements before it, so the count is 0, resulting in res equals 0. For the second number, 1, none of the preceding elements are smaller, so the count remains 0, making res equals 0, 0. For the third number, 2, the only smaller number is 1, so the count becomes 1, updating res equals 0, 0, 1. For the fourth number, another 2, both 1 and the earlier 2 are smaller, giving a count of 2 and resulting in res equals 0, 0, 1, 2. Finally, for the fifth number, 3, the numbers 1, 2, and 2 are smaller, so the count is 3, and the output becomes res equals 0, 0, 1, 2, 3. While this approach is straightforward, it's important to consider its time complexity. Since the outer loop runs n times and the inner loop runs up to I times during the ith iteration, the overall time complexity is O, n squared. The space complexity, on the other hand, is O, n, as we only use the result array for storage. The brute force approach, while simple, has its limitations in terms of performance. Its quadratic time complexity makes it impractical for large input sizes. However, it works well for smaller arrays. There are also some edge cases to consider. For example, if the input array is empty, the output is an empty array. If all elements are the same, the result will be an array of zeros, since no element is smaller than any other. If the array is in ascending order, the counts will increase incrementally, producing 0, 1, 2, and 1. Conversely, if the array is in descending order, every count will be 0, resulting in 0, 0, 0, 0. The brute force approach uses two key data structures, the result array res, which stores the final counts, and the counter variable count, which keeps track of smaller elements during each comparison. While minimal and straightforward, these structures are sufficient to implement the algorithm. Although the brute force approach is simple and intuitive, it becomes inefficient for larger arrays. To optimize this problem, we can use advanced techniques like a binary search tree, a Fenwick tree, or merge sort. A binary search tree allows us to store elements dynamically and count smaller elements in O, log n, time for each insertion, reducing the overall time complexity to O, n log n. Similarly, a Fenwick tree, or binary index tree, can dynamically update and query counts in assorted order, also achieving O, n log n, time complexity. Another efficient approach involves merge sort. During the merge step, we count how many elements in the right subarray are smaller than the current element in the left subarray. This technique leverages the divide and conquer strategy to achieve O, n log n, complexity. These optimized approaches provide significant performance improvements, especially for larger inputs, making them more suitable for real-world scenarios where efficiency matters. This implementation efficiently solves the problem of finding how many numbers are smaller than the current number for each element in the input list. Here's the step-by-step explanation. 1. Sorting the array asterisk. The code begins by creating a sorted copy of the input array nums. Sorting ensures that smaller numbers naturally appear earlier in the array. The sorted function is used for this purpose, which operates in O, n log n, time. 2. Building the dictionary asterisk. A dictionary smaller underscore count is used to store the number of elements smaller than each unique number in the input list. This is achieved by iterating over the sorted array using a for loop. The index I of each number in the sorted array directly represents how many numbers are smaller than it, because the array is sorted. To avoid overwriting values, the dictionary is updated only if the number is not already present as a key. This ensures that we capture the first occurrence of each number, which corresponds to the count of smaller numbers. 3. Generating the result asterisk. The result is generated using a list comprehension. For each number in the original nums array, the pre-computed value from the smaller underscore count dictionary is retrieved. This step is very efficient because dictionary lookups are O1. For returning the result asterisk finally, the result list is returned, containing the count of smaller numbers for each element in the input array. Hashtag efficiency. The sorting step is O, n log n, and the dictionary creation is O, n, since each element is processed once. The final list comprehension is also O, n. Overall, the time complexity of the solution is O, n log n, which is efficient and scales well for large inputs. This implementation is clean, concise, and avoids redundant computations, ensuring optimal performance. This is the Java implementation of the LeetCode problem number 1365. How many numbers are smaller than the current number? The logic mirrors the Python solution using a sorted copy of the input array and a hash map to store the first occurrence of each number in sorted order. The main differences include Java's explicit type declarations, usage of arrays.sort for sorting, and a hash map instead of Python's dictionary. Finally, the result array is built by looking up the count for each number in the map. To solve this problem, we need to find out how many numbers in the input list are smaller than each number in the list. The goal is to generate a result array where each element represents this count for its corresponding number. Let's start with an example. Suppose the input array is nums equals 8, 1, 2, 2, 3. First, we sort the array to get sorted underscore nums equals 1, 2, 2, 3, 8. Sorting helps us determine the relative order of numbers. Next, we build a dictionary called smaller underscore count that maps each number in the sorted array to the number of elements smaller than it. To do this, we iterate through sorted underscore nums, and for each number, we store its index in the dictionary if it hasn't been added yet. For example, at index 0, the number is 1, so we add 1, 0 to the dictionary. At index 1, the number is 2, so we add 2, 1. We skip duplicates, so the next new entry is at index 3, where we add 3, 3. Finally, at index 4, we record 8, 4. The resulting dictionary is smaller underscore count equals 1 o'clock, 2, 1, 3, 3, 8, 4. This dictionary now tells us how many numbers are smaller than each unique number in the original array. Now that we have the dictionary smaller underscore count, we can generate the result array. To do this, we iterate through the original input array nums and look up each number in the dictionary. For example, the first number in nums is 8, and smaller underscore count, 8, gives us 4, so the result for this number is 4. For the second number, 1, the dictionary gives us 0, so the result is 0. For the two occurrences of 2, the dictionary gives 1 for each, so we add 1, 1 to the result array. Finally, for the last number, 3, the dictionary gives us 3, so the result is 3. Putting it all together, the result array becomes 4, 0, 1, 1, 3. Let's look at another example. If the input array is nums equals 6, 5, 4, 8, the first step is to sort the array, which gives us sorted underscore nums equals 4, 5, 6, 8. Sorting ensures we can determine the relative order of the numbers quickly. From the sorted array sorted underscore nums equals 4, 5, 6, 8, we create the dictionary smaller underscore count by iterating through each element and recording its index, just like before. At index 0, the number is 4, so we add 4, 0 to the dictionary. At index 1, the number is 5, so we add 5, 1. At index 2, the number is 6, so we add 6, 2. Finally, at index 3, the number is 8, so we add 8, 3. The completed dictionary is smaller underscore count equals 4 o'clock, 5, 1, 6, 2, 8, 3. Using this dictionary, we generate the result array by looking up each number in the original array. For the first number, 6, the dictionary gives us 2, so the result is 2. For the second number, 5, the dictionary gives us 1, so the result is 1. For the third number, 4, the dictionary gives us 0, so the result is 0. And for the last number, 8, the dictionary gives us 3, so the result is 3. Combining these, the final result array is 2, 1, 0, 3. Now let's consider the case where all the numbers in the input array are the same. For example, if nums equals 7, 7, 7, 7, the sorted array is sorted underscore nums equals 7, 7, 7, 7. Observing this, we see that all the numbers are identical, meaning no number is smaller than any other. To handle this, we build the dictionary smaller_count by iterating through the sorted array. At index 0, the number is 7, so we add 7, 0 to the dictionary. Since all subsequent numbers are duplicates, we don't add anything further. The dictionary is simply smaller_count equals 7 o'clock. Using this dictionary, we generate the result array by looking up each number in the input array. For every occurrence of 7, the dictionary gives us 0, so the result array is 0, 0, 0, 0. This example shows how the approach works even when the array contains duplicates. The solution hinges on 3 key steps: sorting the array, building the dictionary to map numbers to their counts, and constructing the result efficiently using this dictionary. Finally, let's analyze the complexity of this solution. The first step, sorting the array, takes n log n time, where n is the length of the input array. The second step, creating the dictionary, involves a single iteration over the sorted array, which takes n time. The third step, generating the result array, requires another iteration over the original input array, which is also n. Combining these, the overall time complexity is n log n, dominated by the sorting step. This makes the solution efficient for reasonably large inputs. The space complexity is n as well, due to the storage required for the dictionary and the sorted array. By balancing time and space efficiency, this approach provides a robust solution to the problem of counting how many numbers are smaller than each number in the array. To analyze the time complexity of our solution, we start by looking at its main components. First, the sorting step. Sorting the input list using Python's built-in sorted function takes n*log n time. This is because it uses timsort, which is efficient for the average in worst cases. Next, we build a dictionary called smaller_count. For this, we iterate through the sorted list, taking n time in total. Each dictionary insertion or lookup is 1 on average, so this step remains linear. Finally, we generate the result list by performing a dictionary lookup for each number in the original nums list. Since there are n numbers and each lookup is 1, this step also takes n time. Together, these steps give us the time complexity breakdown. Now, combining the contributions of these steps, the overall time complexity is determined. The sorting step, which is n*log n, dominates the process, as it grows faster than the other linear steps. Therefore, the total time complexity of our solution is n*log n. Moving on to the space complexity, we consider the storage required during execution. First, the sorted function creates a new list, which requires n space to store the sorted copy of nums. Next, the dictionary smaller_count stores key value pairs for each unique number in nums. In the worst case, where all numbers are distinct, the dictionary will contain n entries. Since each entry consumes constant space, this step also requires n space in total. Additionally, we need space for the result list, which contains n integers. This requires another n space. Summing these contributions, we have n space for the sorted copy of nums, n space for the dictionary, and n space for the result list. Altogether, the overall space complexity of the solution is n, as all components scale linearly with the size of the input list. This balance between time and space usage makes the solution efficient and practical for large inputs. When comparing this approach to a brute force solution, the improvements become clear. The naive method would involve comparing every number in nums with every other number to count how many are smaller. This results in n squared time complexity, as each of the n elements requires n comparisons. However, the brute force approach does have an advantage in terms of space, using only 1 additional memory since no extra data structures are created. By contrast, our optimized solution reduces the time complexity to n*log n by leveraging sorting, which is significantly faster for large inputs. The trade-off is a modest increase in space complexity to n, due to the use of the sorted list, the dictionary, and the result list. Finally, let's analyze the best, average, and worst cases for this solution. In the best case, where all numbers in nums are identical, the algorithm still performs sorting, dictionary creation, and result generation. Thus, the time complexity remains O, n asterisk log n, and the space complexity is O, n. For average or worst-case scenarios, such as when all numbers are distinct, the time and space complexities remain consistent at O, n asterisk log n, and O, n, respectively. This is because the sorting step dominates the time complexity, as O, n asterisk log n, grows significantly faster than O, n, as n increases. Similarly, the space usage is linear since all additional data structures scale directly with the input size. Overall, this optimized solution strikes an excellent balance, vastly improving time efficiency compared to the brute force method while maintaining reasonable space usage. In this problem, there are a few common mistakes to watch out for. First, not accounting for duplicate elements can lead to incorrect results. For instance, if the array contains 2, 2, 3, treating both 2s as unique values might double count smaller elements, which is incorrect. A good way to avoid this is by using a hash map to store the frequency of each value or by ensuring duplicates are properly handled during comparisons. Another mistake is using inefficient nested loops in large arrays. A brute force approach with O, n squared, complexity might seem straightforward, but if the input size is large, say 10,000 elements or more, it will result in a time limit exceeded error. Instead, you can optimize by sorting the array or leveraging efficient data structures like binary index trees or segment trees, both of which reduce complexity. Finally, misinterpreting the problem statement is another frequent pitfall. A common example is confusing smaller numbers with smaller numbers at earlier positions. To avoid this, always read the problem statement carefully and verify your understanding with examples before jumping into the solution. Another area to be cautious about is edge cases. For example, arrays of size 0 or 1, or arrays where all elements are identical, can result in runtime errors or incorrect outputs if not handled properly. Testing your solution against these boundary conditions ensures robustness. Additionally, overcomplicating the logic can lead to unnecessary errors. Sometimes, candidates use overly complex data structures or perform redundant computations, which can make the solution harder to debug and less efficient. The key here is to strive for simplicity. Start with a clean approach and build incrementally, testing small parts as you proceed. A simple, well-tested solution is often better than a convoluted one. When preparing for interviews, it's helpful to recognize that this problem belongs to a broader category of counting smaller or larger elements problems. Solutions to these often involve patterns like sorting, binary search, or tree-based data structures, so identifying these patterns can give you a head start. It's also important to understand the trade-offs between approaches. While a brute force solution might be quicker to implement, it's rarely the optimal choice. Sorting-based methods, which have a complexity of O, n log n, often strike a good balance between simplicity and efficiency during interviews. As you explain your approach, make sure to clearly communicate your thought process. For instance, justify why you chose a particular method, like merge sort, instead of a binary index tree. If time permits, you can also discuss how advanced data structures, like segment trees, could further optimize the solution, even if you don't implement them. This shows a depth of understanding that interviewers appreciate. This problem is closely related to several other LeetCode questions. For example, in LeetCode 3.15, count of smaller numbers after self, you're tasked with counting smaller elements to the right, which is a variation of the current problem. Other related problems include LeetCode 4.93, reverse pairs, and LeetCode 3.27, count of range sum. Exploring these problems can help you deepen your understanding of similar patterns and techniques. One alternative approach to solving this problem is sorting combined with binary search. Here, you sort the array first, and then for each element, use binary search to count how many smaller elements exist. This method has a complexity of O, n log n, for sorting and O, n log n, for the binary search steps. While this is more efficient than brute force, it does require extra space for storing the sorted array. This trade-off makes it a practical choice in many scenarios. There are also more advanced approaches that use data structures like Fenwick trees or segment trees. With a Fenwick tree, you maintain frequency counts in a compressed index space, allowing for efficient updates and queries. This approach has a time complexity of O, n log n, and is very efficient, but it requires familiarity with Fenwick trees, which can be challenging for some. Similarly, a segment tree can be used to maintain range frequencies, offering the same O, n log n, complexity for both construction and queries. While more flexible than a Fenwick tree for range queries, it involves more overhead in implementation. Finally, a merge sort modification is another elegant solution. By modifying the merge step to count smaller elements, you can achieve optimal efficiency with O, n log n, complexity. This method is often easier to implement than tree-based approaches, but it does require careful handling of indices during the merge phase. Each of these methods has its trade-offs, so choose the one that best fits the context of the problem and your familiarity with the tools. Great job! To summarize, we tackled the problem by analyzing different approaches, including brute force and an optimized solution using sorting and hash maps. Remember the importance of efficiency and edge case handling. Thanks for watching, and see you in the next coding challenge. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!